today I'm going to explain about the standardizing. And the reason why we have to standardize the normal random variable is that there are numerous normal random variables with different means and variances. So it is impossible to calculate all the cumulative normal distribution. So we can simply use this standardizing method to use the appendix table. Okay? So this appendix table is the cumulative standard normal distribution based on this standardizing method. So if x is a normal random variable with mean and variance, the standard normal random variable will be z is equal to x minus mu over sigma. So z is a normal random variable with mean is equal to 0 and the variance is equal to 1. So the standard normal random variable will have this kind of distribution function, and in this case the mu is equal to 0 and the variance sigma square is equal to 1. Okay? So no matter the normal random variable is, by using this equation we can use this formulation based on the table that I gave to you. So z is called as a standard normal random variable. Suppose that x is a normal random variable with mean and variance, then the probability of x, which is the normal random variable, should be smaller than or equal to small x. That is equal to the probability of x minus mu over sigma, that is smaller than or equal to small x minus mu over sigma. And that is equal to the probability of z, which is the standard normal random variable, and should be smaller than or equal to small z. So where z is a standard normal random variable, and small z can be expressed by x minus mu over sigma. So this is the example. For the normally distributed current, the current measurement in a strip of wire are assumed to follow a normal distribution with mu is equal to 10 milliampere and sigma square is equal to 4 milliampere square. And what is the probability that a measurement will exceed the 13 milliamperes? So we have to calculate the probability of x when x is larger than 13, right? And based on the previous equation, this can be changed to the probability of x minus mu over sigma should be larger than 13 minus 10, right? Because here mu is 10 over 2. Right? The sigma square is 4 milliampere square, so the sigma will be 2. So this can be rewritten as the probability of z, which is the standard random variable, right? Standard normal random variable. That should be larger than 3 over 2. Okay? That is equal to the probability of z when z is larger than 1.5. Okay? In that case, z is the standard normal random variable. And so we can use this description, right? In this case. And this will be this shaded area, right? So if we want to use the table, appendix table, this should be changed to 1 minus probability z when z is smaller than or equal to 1.5, right? So by using the table, that can be 1 minus 0.93319. That is equal to 0.06681. Okay? So we can simply calculate this example based on the standardizing method. Continuing the previous example, what is the probability that the current measurement is between 9 and 11 milliamperes? In this case, we have to calculate the probability of x when x is between 9 and 11 milliamperes, right? And this also can be changed to the standard normal random variable between 9 minus 10 over 2, 11 minus 10 over 2, right? Okay? And this can be the probability of z when z is between minus 0.5 and plus 0.5, right? And this will be the probability of z when z is smaller than 0.5 minus the probability of z when z is smaller than minus 0.5, right? Because for this case, we have to calculate this shaded area, right? Right? For this case. So we can use this equation, right? First, we can calculate the probability of z when z is smaller than 0.5 minus the probability of z when z is smaller than minus 0.5. So we can calculate this shaded area, okay? So based on the appendix table, this will be 0.69146 minus 0.30854. That is equal to 0.38292. Okay? Okay. So by using the appendix table and the standardizing method, we can simply calculate the cumulative probability. And this is another example. Assume that in the detection of the digital signal, the background noise follows a normal distribution with mu is equal to 0 and sigma is equal to 0.45. The system assumes a digital one has been transmitted when the voltage of noise exceeds 0.9. What is the probability of detecting the digital one? In this case, we can assume that the random variable n denotes the voltage of noise. So there should be the probability of n should be larger than 0.9, right? To detect the digital one here, right? Because the system assumes a digital one has been transmitted when only the voltage of noise exceeds 0.9. So we have to find out this value. And also we can use the standardizing method. N minus mu over sigma should be larger than 0.9 minus 0 here, right? 0 over 0.45. Okay? So this can be the probability that normal random variable z when z is larger than 2. Okay? So this will be 1 minus probability of when z is smaller than or equal to 2. Okay? So the answer will be 0.0225. Okay? And suppose that when a digital 1 signal is transmitted, the mean of noise distribution immediately shifts to mu is equal to 1.8 volts. Which means that when the digital 1 signal is transmitted, the mean of the noise distribution is changed from 0 to 1.8 volts. Okay? Let S denote the voltage when a digital 1 is transmitted. And what is the probability that the digital 1 is not detected? In this case, the probability of S should be smaller than 0.9, right? Right? Why? Because we have to find out the probability that the digit 1 is not detected, which means that the noise distribution should be smaller than 0.9. Okay? So we have to calculate this. So we can change this to standard normal random variable S minus mu over sigma should be smaller than 0.9 minus 1.8, right? Because mu is changed from 0 to 1.8 volts. Okay? Right? So that over 0.45. So that is equal to the probability of z when z is smaller than minus 2. Right? The answer will be 0.0275. Okay? Okay? So we can find out this answer from this example. And this is the last example. The diameter of the shift of the shaft is normally distributed with the mean is equal to 0.2508 inch, and the standard deviation sigma is equal to 0.00005 inch. The specifications on the shaft are 0.25 plus minus 0.0015 inch. Let x denote the shaft diameter in inches and what proportion of shaft conforms to the specifications. In this case, we have to find out the probability of x when x is between 0.2485, 0.2515, right? Why? Because the specifications on the shaft are 0.25 plus minus 0.0015. So the proportion of shaft which conforms to the specification should be between 0.2485 and 0.2515, right? And this can be rewritten as the probability of z when z is between 0.2485 minus what is the mean? That is 0.2505, 0.2508 over 0.0005. That is 0.2515 minus 0.2508 over 0.0005. Okay? So this value will be the probability of z. Z is between minus 4.6 and 1.4. Okay? This will be the probability of z when z is smaller than 1.4 minus the probability of z when z is smaller than minus 4.6. Okay? And this value will be 0.919243. And what about this one? And as you can see in the table, the last value is minus 3.99, right? But this value is higher than the last value in the table, which means that we can simply apply the 0. Okay? So if you have the value smaller than minus 3.99, you can calculate the probability is equal to 0. And what about the plus case? The maximum value is 3.99, right? And if you have the value larger than 3.99, you can have the probability of 1. Okay? Because the value is very close to the 1. So the answer will be just this value. Okay? And if the mean is equal to the target value, mu is equal to 0.5, what proportion of the shaft will now conform? In this case, we have to find out the probability of x when x is between 0.2485 and 0.2515. But in this case, the mu was changed, right? From 0.2508 to 0.25. So this can be changed to 0.24, 0.25 over 0.0005. That's 0.2515 minus 0.25 over 0.0005. Okay? This will be the probability of z. And z is between minus 3 to plus 3. And this will be the probability of z when z is smaller than 3 minus the probability of z when z is smaller than minus 3. So the answer will be 0.9973. So this is the end of the scope of the midterm exam. Okay. So I'm going to solve the assignment first and second. Okay. Assignment 1 and 2. So this is the assignment number 1, and this is the first question. Suppose your vehicle is licensed in a state that issues license plates that consist of three digits between 0 and 9 and followed by 3 letters between A and Z. And in this case, we can first have 3 digits, right? The first 3 part will be 3 digits. This will be digits from 0 to 9, okay? And the followed 3 parts will be the letters, okay? From A to Z, right? And in the case, what is the probability to select the first digit here? The total number here is 10, right? And the total letters here is 26, right? So the probability of selecting the first digit will be 1 over 10, right? And what about the second part? That is also has the probability of 1 over 10, right? And this is also the same probability, 1 over 10. And what about this? The probability of selecting the fourth part, there will be 1 over 26, right? Because the total number of letters is 26. This is also 1 over 26, and this is also 1 over 26. And this 6 part should be connected as AND condition, right? Because we have to find out just one licensed plate. So this should be connected as AND condition. So the probability will be 1 over 10 to third power multiplied by 26 to third power. So this will be 5.7 multiplied by 10 to minus 8th power. Okay? That is the probability. So that is the answer for the first question. And this is the second question. Customers are used to evaluate the preliminary product design. In the past, 95% of highly successful products received good review, and 60% of moderately successful products received good reviews, and only 10% of poor products received good reviews. In addition, 40% of products have been highly successful, and 35% have been moderately successful, and 25% have been poor product. So if we denote H as the highly successful product. What is the probability of H? That is 0.4, right? Right? And if we denote M as a moderately successful product, the probability of M should be equal to 3.5, right? And the probability of P, which is the poor product, will be 0.25, okay? And the first question is that what is the probability that a product attain a good review? And we can denote G as a good review, okay? So, in this case, we have to find out the probability of G, good review, right? And that can be the summation of the probability of the intersection of H and G plus the probability of intersection of M and G plus the probability of the intersection of P and G, right? Right? Because we can have the good review, but we have three levels of the product. First one is the highly successful product, and second one is the moderately successful product, and the third one is the poor product. And we have three options, right? So to have the total probability of the good review, we have to add all these three combinations, right? Right? And this can be changed to the conditional probability of G given H multiplied by the probability of H, right? Right? And this can be changed to the conditional probability of G given M multiplied by the probability of M. And this can be the conditional probability of G given P multiplied by the probability of P. So what is the conditional probability of G given H? That is 95%, right? So 0.95 multiplied by 0.4, okay? Plus, what is the conditional probability of G given M? That is 0.6. 0.6 multiplied by 0.35 plus 0.1 here, okay, 10%. 1 multiplied by 0.25. So if you solve this, we can obtain 0.615. Okay? This is the probability of obtaining the good review. And if a new design attains a good review, what is the probability that it will be a highly successful product? This is the conditional probability, right? This will be the conditional probability of H given G, right? Because we have to find out the highly successful product when we obtain a good review. So this is the conditional probability. And as I already explained, the order is not important for this case. So this can be the conditional probability of G given H multiplied by the probability of H over the probability of G. Okay? So this can be 0.95 multiplied by 0.4 over 0.615. The answer will be 0.618. Okay? And this is the third question. If a product does not attain a good review, what is the probability that it will be a highly successful product? This is also the conditional probability, right? For this case, we have to calculate the conditional probability of H given the complement of G, right? Right? Why? Because the product does not attain a good review. Okay? So this also can be expressed by the conditional probability of G prime given H multiplied by the probability of H over the probability of G prime. Right? And what is the conditional probability of G prime given H? That is 0.5, right? Right? 0.5. 0.05, sorry. Right? And the probability of H is 0.4 over, what is the probability of G prime? That is 1 minus 0.615. Okay? So this will be 0.05 multiplied by 0.4 over 0.385. The answer will be 0.052. Okay? So we can solve the second question also. And this is the third question. A steel plate contains 20 volts. Assume that 5 volts are not torqued to the proper limit, and 4 volts are selected at random without replacement to be checked for torque. And what is the probability that all 4 of the selected volts are torqued to the proper limit? And we can use the combination rule, right? Because the order is not important and without replacement. So what is the numerator for this case? That is, we have to find out the probability that all 4 of the selected volts are torqued to the proper limit. That means this is the combination of 15 by 4. That is the total number of cases that we can select 4 volts with a proper limit. Okay? And we have to find out the probability. So what should be the denominator? There will be the combination of 20 to 4. Okay? So this is the total number of cases that we can select any 4 volt, right? And this is the number of cases, total number of cases that we can select 4 volt with a proper limit. Okay? So by dividing these two things, we can obtain the probability. Okay? So this will be 15 factorial over 4 factorial multiplied by 11 factorial over 20 factorial over 4 factorial multiplied by 16 factorials. And this will be 15 by 14 by 13 by 12 by 11 factorial over 4 by 3 by 2 by 1 by 11 factorial over 20 by 19 by 18 by 17 by 16 factorial over 4 by 3 by 2 by 1 by 16 factorials. Okay? So 11 factorials can be eliminated first. And 4 by 3 can be eliminated by dividing 12. Okay? And 2 can be eliminated by dividing 14 by 2. And 7 will be left here. So this will be the 15 multiplied by 7 multiplied by 13. And in this case, 16 factorials can be eliminated, right? And 4 can be eliminated by dividing 20, and 5 will be left. And 3 by 2 can be eliminated by dividing 18, and 3 will be left here, right? So this will be 5 multiplied by 19 multiplied by 3 multiplied by 17. And this will be 1,365 over 4,845. So the answer will be 0.282. Okay? So that is the answer for this question. And what is the probability that at least one of the selected bolts is not torqued to the proper limit? In this case, we can denote B as and we can denote that B is a case that at least one of the selected bolts is not torqued. Okay? And in this case, we have to find out the probability of B, right? And this can be written as 1 minus B probability of B prime. Okay? What is the B prime here? 4 bolts are torqued properly, right? And so what is the probability of B prime? That is the answer of A. Okay? So this can be 1 minus 0.282. So the answer will be 0.718. Okay? Okay? So this is the answer for the third question. And this is the number 4. A batch of 25 injection molded part contains 5 parts that have suffered excessive shrinkage. If 2 parts are selected at random and without replacement, what is the probability that the second part selected is the one with excessive shrinkage? If we denote that A is the case that the first part has excessive shrinkage, and B denotes that the case that the second part has excessive shrinkage. And in this case, what is the probability that the second part selected is the one with excessive shrinkage? We have to find out the probability of B, right? Right? Because we denote B as the case that the second part has excessive shrinkage, okay? And this can be the summation of the probability of A, the probability of the intersection of A and B, and the probability of the intersection of A prime and B, right? Because we have 2 options. That the first one is that the first part is also has excessive shrinkage, right? Right? But on the other hand, the first part doesn't have excessive shrinkage. Okay? 그러니까 저희가 지금 두 번째가 excessive shrinkage를 갖고 있는 것을 뽑을 확률이잖아요. 그러면 첫 번째는 excessive shrinkage일 수도 있고 아닐 수도 있어요. 그죠? 그죠? 근데 이 두 가지 초이스가 다 선택이 될 수가 있죠. 확률은 두 가지 다 더해야 될 거 아니에요. 이 경우도 되고 이 경우도 되니까. 그죠? 근데 이 두 가지가 될 경우에는 컨비네이션이죠. 아니, 컨비네이션 아니고 인터섹션이죠. 교집합이죠. So, this can be changed to the conditional probability of B given A multiplied by the probability of A plus the conditional probability of B given A prime multiplied by the probability of A prime. Okay? So, in this case, what is the conditional probability of B given A? The A was already selected, right? So there are only 24 injection mold, right? Injection molded part. Right? So the denominator should be equal to 24. And A is the first part has excessive shrinkage. That means we have only 4 parts left. So there will be 4 over 24, right? And what is the probability of A? There will be 5 over 25, right? Okay? Because A indicates the case that the first part has excessive shrinkage, and we have a total 25 parts, and among them, 5 parts have suffered excessive shrinkage. So the probability of A will be 5 over 25, right? 그죠? 왜냐면 저희가 지금 5개 파트가 excessive shrinkage이고요. 총 25개가 있어요. 그러면 요 첫 번째 걸 뽑았을 때 그게 excessive shrinkage일 확률은 5 나누기 25죠. 그죠? 그리고 conditional probability 같은 경우는 A가 이미 발생했잖아요. 그러면 25개 중에 일단 하나가 뽑힌 거고요. 그래서 24가 되고, 그리고 5개 중에 excessive shrinkage가 있는 5개 중에 하나가 이미 뽑혔잖아요. 그죠? 그럼 남아있는 게 4개죠. 그럼 4 나누기 24가 돼야 되겠죠. 아시겠죠? And what about the conditional probability of B given A prime? There will be 5 over 24. Right? Right? And what is the probability of A prime? There will be 20 over 25. Okay? So the answer will be 0.2. And this is another question. If part are flipped and random without replacement, what is the probability that the third part selected is the one with excessive shrinkage? In that case, we can denote C is the case that a third part has excessive shrinkage. Okay? And to calculate this, I'm going to use the tree diagram, okay, to explain the equation. This is the first part. We have two options, right? Non-excessive or excessive, right? And what is the probability of the non-excessive? That is 20 over 25, right? And the probability of E will be 5 over 25. Okay? And we also have the second part. We also have two options. Non-excessive, excessive, right? And also non-excessive, excessive. Okay? And what is the probability of the non-excessive for the case of this second part? This will be 19 over 4, right? That is the conditional probability. Do you remember that? Because the non-excessive case was selected in the first part, right? And then we can select the non-excessive part with this probability. Because 1 is already selected here, right? So the denominator should be equal to 24, right? The numerator should be equal to 19. Okay? So this is the conditional probability. So the first part is already selected. And we can have this case at the second part. Okay? 지금 이 트리 다이어그램에서 보면 이게 첫 번째 파트가 두 가지로 나뉘죠. 그리고 세컨드 파트가 또 두 가지로 나뉠 수가 있는데 각각의 경우에 또 두 가지가 되니까 총 4가지 경우가 돼요. 그죠? 근데 이 경우에는 이미 첫 번째에서 하나 뽑았는데 그게 non-excessive였어요. 그러면 20개 중에 한 개가 이미 뽑힌 거죠. 그러면 분자는 19가 되겠죠? 그죠? 그리고 총 25개 중에 이미 하나 뽑혔잖아요. 그럼 분모는 24가 되겠죠. 오케이? 그래서 이게 conditional probability 룰이잖아요. 그죠? So what about this case? That is 5 over 24, right? Because the part with excessive shrinkage was not selected at the first part. Okay? Okay? So, in that case, the conditional probability will be 20 over 24, right? This will be 4 over 24. Okay? And we can consider the third part. We also have two options. Also, there will be non-excessive, excessive, non-excessive, excessive, non-excessive, excessive, and excessive. And what is the probability for this case? That is 18 over 23, right? And what about this case? That is 5 over 23, right? Because for the first part and the second part, the part with excessive shrinkage was not selected yet. So there are still 5 parts with excessive shrinkage in this case. Okay? So the probability will be 5 over 23. And what about this case? That is 19 over 23, right? Right? Because the first part selected was non-excessive shrinkage, but the second part selected has the excessive shrinkage. So there are only 19 parts with non-excessive shrinkage, okay? Among 23. And this can be 4 over 23, right? Right? And this will be 19 over 23. And this will be 4 over 23. And this will be 3 over 23. Okay? Okay? And the question was, what is the probability that the third part selected is the one with excessive shrinkage? That is, we have to obtain these 4 cases, right? So the probability of E will be 20 over 25, 19 over 24, and 5 over 23 plus 20 over 25, 5 over 24, and 4 over 23 plus 5 over 25, 20 over 24, and 4 over 23 plus 5 over 25 and 4 over 24 and 3 over 23. Okay? Okay? So, if you calculate this equation, the answer will be 0.2. Okay? And for this case, what is this? That is the probability of A. And what is this? That is the probability of A prime. Okay? What is this? That is the conditional probability of B prime given A prime. Right? And this, the conditional probability of B given A prime, right? And this will be the conditional probability of B prime given A. That is the conditional probability of B given A. Okay? And what is this? For this part, these two cases can be expressed by the probability of the B prime, right? Right? What about this point? That is the probability of A prime intersection B, right? Okay? And what about this? That is the probability of intersection of A and B prime. And for this, there is a probability of intersection of A and B. Okay? So finally, this can be written as the conditional probability of C given A prime intersection B prime multiplied by the probability of A prime intersection B prime, right? Why? This can be expressed by this conditional probability. Okay? Okay? And this conditional probability should be multiplied by the previous case. Okay? That is the probability of the intersection of A prime and B prime. Okay? Plus the probability, the conditional probability of C given A prime intersection B multiplied by the probability of intersection of A prime and B plus the probability of the conditional probability of C given A intersection B prime multiplied by the probability of the intersection of A and B prime plus probability of the conditional probability of C given A intersection B multiplied by the probability of the intersection of A and B. Okay? So when we have the three cases, we can use this equation. Okay? Based on this tree diagram. So this is the end of the assignment number 1. And I'm going to solve the assignment number 2. We don't have enough time. I'm going to solve only the second question, okay? Assume that each of your calls to a popular radio station has a probability of 0.02 of connecting. The P is equal to 0.02. And assume that your calls are independent. And what is the probability that your first connected call is your 10th call? That is geometric random variable, right? So for the case of the geometric random variable, the probability of x when x is equal to small x can be 1 minus p to x minus 1's power multiplied by p. This is the equation for the geometric random variable. And in this case, we have to find out the probability that our first connected core is our 10th core. That means the probability of x is equal to 10, right? So this can be 1 minus 0.02 to 9th power multiplied by 0.02. Okay? So this will be 0.988 to 9th power multiplied by 0.02. So the answer will be 0.0167. And what is the probability that it requires more than 5 cores for you to connect? We have to calculate the probability of x when x is larger than 5, right? So this can be 1 minus the probability of x when x is smaller than or equal to 4. That can be 1 minus the probability of x when x is equal to 1, and the probability of x when x is equal to 2, the probability of x when x is equal to 3, and the probability of x when x is equal to 4. Okay? more than. 맞죠? 5보다 크. 아. More than 5 cores. It requires more than 5 cores. It requires more than 5 cores. And need to connect. 여기서는 이상이라고 봐야 돼요. 이상. 이상. more than이 5 core보다 크거나 같다라고 봐야 되는데 번째까지 5개보다 더 크다. 여기가 equal이 들어가야 되는데 more than은 이거보다 크다잖아요. 그죠? 뭐보다 크다인데 이 문제에서는 equal이 들어가야지 맞게끔 사실 되어 있거든요. 그러니까 요거는 둘 다 맞게 해줄게요. 그러니까 5까지 포함한 사람도 맞게 해줄게요. 4 이하로 한 사람도 맞게 해주고. 아시겠죠? 오 5보다 커야 됩니다. 그러면 6번째부터니까 5개까지 5번까지 있어야 된다. 이거는 이게 맞겠네요. 이게 5보다 커야 돼. more than이니까 5보다 커야 되고요. 그렇기 때문에 1-x-5보다 작거나 같다로 바뀌어야 돼요. 아시겠죠? 근데 이거는 4로 한 사람도 일단 숙제에서 맞게 해줄게요. 아시겠죠? 근데 만약 문제에서 more than이 나오면 이거보다는 그러니까 등호 없는 걸로 생각하셔야 됩니다. 이것보다 커야 되니까. 아시겠죠? 아시겠죠? 또는 more than or equal to가 들어가면은 부등호가 되겠죠? 아시겠죠? So this is the answer for this question, okay? So this is the last question. What is the mean number of cores needed to connect? The mean mu is equal to 1 over p, right? So that is 1 over 50. Okay? So this is end of today's class. And see you on Friday. Okay? Good luck.